everybody. First of all, I would like to thank Fast Eddie for improving my blood sugar and for improving the blood sugar of all of you. I'd also like to thank Matt, and Phil for organizing this conference for the 5th year. It's really amazing to have all of you here and see all of you, the audience growing. So thank you. Yeah, definitely a round of applause. My name is Shawn Przybilla. I'm a solutions architect for the media and entertainment vertical at AWS, and I'm joined by John Saxton, an SDE and mean poker player from the AWS Elemental Media Services team. Today we want to spend a bit of time talking about how we handle reliable live streaming. And I think before we get into the technical details, I wanted to set up a little bit of context on what reliability means for us and our customers and for all of you when you're implementing these types of solutions. So when, in my experience, I've worked in this industry for about 10 years, and I've done everything from streaming operating rooms to doctors to streaming conferences like this, and now streaming major sporting events for our customers. And I've realized that reliability means a lot of different things to a lot of different people. And for the purposes of this talk, I want you to put yourself in the perspective of a premium rights holder, somebody who's paid millions of dollars to redistribute content on the internet, and their entire livelihood really depends on this stream staying up and having a really awesome end user experience for all of their viewers, regardless of what happens in the infrastructure on the back end. And so think about the large events you've watched on the internet with millions of concurrent viewers, events that might have major revenue implications, maybe major rights implications, and think about how we're engineering reliability as it pertains to content delivery as the core business for a major media company. Just a little context from a technical perspective, in case anybody isn't working on live streaming systems. I'm sure all of you are, but just a little baselining before we get into the technical details. There's kind of a few main phases. We have obviously some sort of system at the stadium or the event site or at a venue like this one that's capturing, producing, mixing the feed. I think there's a switcher back there in the corner. Might look a lot like that. There's probably a video encoder involved that's contributing a feed to some type of back-end infrastructure. That infrastructure is probably encoding to adaptive bitrate, HLS, dash, smooth, etc. And then we'd have a system to host or originate that content. Some type of CDN to deliver that content, and then finally some type of player experience or application to present that content to our end users. But as we know, as engineers, and as Werner, the CTO of Amazon, knows, everything fails all the time, and that's where we want to spend the remainder of this talk, specifically focused on the infrastructure components, the encoder and the origination services, and how we can manage failure and not impact the end user experience. So if we had built an architecture like this one and we had failure in either the encoder or the origin server, our end user experience might look something like this. And that's terrible. And it's almost 2020, and we're promised flying cars and jetpacks. The least we can do is make sure that if people want to watch content in real time, we provide the infrastructure that allows them to do that. And so a logical approach to implementing reliability in an application like this would be to simply add more infrastructure, right? Like we can add, redundant encoders, switchers at the event site. We can add, additional encoders in our data centers. We can add additional origin software. We can, add multiple CDNs. But then the problem becomes how do we manage failure across these components and the state that needs to be transferred between those components to ensure the best playback experience for the customer. And so to talk more about specifically the encoder's role in reliable live streaming, I'd like to pass the mic over to John.
Yeah, so let's take a look at what the end user experience looks like now that we've got redundant encoders. So we've got two encoders, A and B, and there's going to be a watermark here in the lower right-hand corner. And you're going to see the motorcycle. It's going to go around the corner, and then encoder A is going to fail. And then you can see that there was a discontinuity there. This is still a pretty good experience, but I think we can do better. Let's take a look at that one more time. It goes around the corner, encoder A fails about here, and there's a glitch. And the reason there was a glitch, we're going to use HLS in most of this presentation, but these concepts can be applied to any other protocol. The reason there was a glitch is because the player consumed segments 10 and 11 from the top encoder and segments 12 through 14 from the bottom encoder. Since the encoders weren't synchronized, we saw a discontinuity. In the previous example, it was a backwards discontinuity, so we saw a bit of repeated content. But the discontinuity could be in the opposite direction, which could result in skipped content. That could be a skipped goal if you're watching a hockey match, for example. With that said, this was still a pretty good experience, but that's just because the encoders happen to be close together. If the encoders were further apart, we'd see a bigger discontinuity, and that's not a good experience. And so to solve this problem, we need to synchronize the encoders. The goal is for segments to be interchangeable. A player should be able to consume segment 3 from either the top encoder or the bottom encoder, and the experience should be the same either way. So how do we know that the segments have the same content? Our encoder synchronization algorithm, which we call output locking, uses the input timecode as a frame identifier. Since both instances of segment 3 have the same input timecode, they should have the same content, and they should be interchangeable. The way this algorithm works is when the bottom encoder starts up, it gets a message from the top encoder saying, I encoded segment 2 at this specific input timecode. The bottom encoder knows that the segment length in this example is 2 seconds. So the bottom encoder can do math and calculate segment 3 is going to start on this specific timecode. And then it just waits until that timecode to start its encode starts on segment 3 instead of segment 1, and we have synchronized encoders. It's worth noting that this algorithm synchronizes more than just segment numbers and segment contents. We're synchronizing metadata like timestamps and outgoing time codes, and manifest metadata like program date time. It's also worth noting that this algorithm has no dependency upon the wall clock at all. We're not looking at frame arrival times. We're not guaranteeing that the two encoders are going to write out the segments at the exact same time. We only guarantee that when the encoders do eventually write out the segments, they're going to be interchangeable with each other. And let's take a look at what this experience looks like. Again, we have two redundant encoders, A and B. You can see the watermark. They're going to hit this jump, then they're going to hit this jump, and encoder A is going to fail. But there was still a little bit of a glitch. Let's watch that one more time. Again, they hit the jump. When he hits the second jump, there's a little bit of a glitch. And the reason there was a glitch was because there's nothing preventing the two encoders from drifting after this initial sync. This can happen for any number of reasons. Input disruptions, input switching, clock drift. We try to minimize this, but it can still happen. If you've studied distributed systems, you're probably familiar with the CAP theorem. And that basically states that you can't build a consistent, highly available system that's also partition tolerant. You either have to compromise on consistency or you have to compromise on availability. Our goal when designing the system was high availability, so we compromised on consistency. So encoders can drift apart, and output locking is a detect and recover algorithm that will detect that the encoders have drifted out of sync and then bring them back in sync. The way that output locking knows that two encoders are out of sync is it has this notion of status. So each encoder has status. For each segment, that segment's going to have metadata associated with it, things like input timecode, as shown on the display. There's also things like timestamps, timecodes, things of that nature that I mentioned earlier. Both encoders are exchanging these status messages with each other. So both encoders have visibility into the global state of the system, and both encoders can see that the system is out of sync. One of the encoders has to resync. Output locking has a series of rules and heuristics to decide which encoder resyncs and which encoder continues running open loop. In this case, encoder B is going to resync and encoder A is going to continue running open loop. Several things happen upon a resync, but the most important thing is that the resyncing encoder is going to adjust its segment size to realign the encoders. In this example, you can see that segment 3602 is out of sync. Then the bottom encoder creates a slightly shorter segment, and then the system is back in sync going forward. And let's take a look at what the end user experience is. Again, two redundant encoders, A and B, and again, when he hits this jump, it's going to fail over. There is no glitch at all. An encoder failed, we failed over, and there was no impact on the end user's quality of experience. Let's look at that one more time.
You can look at it a third time if you want, John.
Okay, I think I will. It's really satisfying.
Good work, John. John spent a large majority of his life working on this feature, so.
So satisfying. Now that we have synchronized encoders, how do we configure our end-to-end workflow to take advantage of this redundancy? Apple provides some guidance on how to do this. In this workflow, we've got two encoders writing to two independent static origins. These are just simple HTTP servers. And then there's a combined master manifest that references the stream manifests from both the top encoder and the bottom encoder. The player downloads that combined master manifest, and then it has visibility into both encoders, so if one fails, the player can just fail over to the other encoder. Here's an example of what that master manifest looks like. I lifted this straight from Apple's website. We've got two renditions, a low rendition and a high rendition. And for each rendition, we have two stream manifests, one pointing to encoder A and one pointing to encoder B. I ran a test with two Elemental live encoders writing to media store. Encoder A wrote to the A subdirectory, encoder B wrote to the B subdirectory. I put an Nginx reverse proxy between the player and the origin, and you can see the access logs. The player is initially playing the high rendition from encoder A, then encoder A fails, and the player fails over to encoder B like you would expect. It's worth noting that even though the encoder failed, the origin didn't fail, so we're still getting 200 status codes on all of our requests. And the only reason the player was able to detect that the encoder failed is because it had a stale manifest detection algorithm. If a player doesn't have a stale manifest detection algorithm, like in this example, playback will effectively stop, even though there's a redundant encoder available. Even though not all players have stale manifest detection, every player we have tested with will fail over if it gets a 404 on the stream manifest. So in this example, I configured an Elemental Media Store Object Lifecycle policy to delete the stream manifest if it goes stale. This is a simple timer-based mechanism. If the manifest hasn't been updated in n seconds, delete it. And you can see how it works. Encoder A, the client's initially pulling from encoder A. Encoder A fails, so it stops sending manifest updates to the origin. The origin detects this, deletes it. The client eventually gets a 404, and it uses that as a signal to fail over to encoder B. Client-side failover is a totally valid approach, but qualifying that workflow can be a challenge since you'll likely want to test that failover works on every device you want to support. If you have a dynamic origin like a packager in your workflow, it can handle encoder failover instead. In this example, we have two encoders writing to a single dynamic origin. And then that dynamic origin exposes a single master manifest with a single set of stream manifests. If one of the encoders happens to fail, the packager can fail over from one encoder to another, and that's totally transparent to the end user. It just plays it back like any other HLS presentation. Media package has a redundant ingest feature that can be used to implement this workflow, and there are other packagers that have similar features that can be used to implement this workflow as well. You might be looking at this and you might be thinking, this packager looks like a single point of failure. And if you're using it depends on which packager you're using. So if you're using media package, you can have a single logical packager with built-in redundancy and you don't need to run multiple instances of it. If your packager doesn't have that built-in redundancy, you would probably want to run multiple instances of it with a load balancer or something in front of it. You might also be wondering, why would anyone ever use a static origin? And static origins can minimize cost and latency. So they make sense in some workflows, but there's not a one-size-fits-all solution, and so output locking supports both.
Cool. And so John talked a lot about the different approaches, predicated mainly on an encoder synchronization algorithm like output locking. And then there's different approaches depending on whether you want to use a static origin or a dynamic origin. So we thought it would be helpful to highlight an application of those concepts with Zach and Flavio's work at CBS, who actually used some of these concepts to build this for Super Bowl 53. So essentially, they were in exactly that kind of use case I mentioned earlier. This CBS only has the rights to redistribute this Super Bowl online once every 3 years. They have somewhere around 2.7 million concurrent viewers to this application. And in their case, they were taking feeds into two data centers, one in New York and one in Connecticut. Those were actually encoding appliances that were in output locked groups. So as we talked about earlier, they were sharing state between those encoders, resynchronization algorithm kicking in if they drifted out of sync. And those encoders were publishing to, in this case, a static origin, AWS Elemental Media Store in US East and US West. And then in front of that, they had a fleet of an origin shield by Fastly, as well as a multi-CDN approach to allow them to essentially dynamically load balance kind of edge delivery of the content that was being served from those origins. If you have any questions about specifics on how they implemented it, I would highly recommend you ping Flavio or Zach in the Slack channel. We don't have time to go into that today, but we thought it was interesting to see some of the concepts applied to a real-world application.
Cool. Yeah, we've only scratched the surface today. There are a lot of additional topics we could discuss if we had time. For example, most of the examples we looked at today had 2 encoders, but there's no reason why this algorithm can't be extended to support multiple encoders. If you're going to support multiple encoders, what's the right communication bus, and how do you handle encoder discovery? That communication bus is going to have latency. How do you handle that? And there are going to be timing differences between encoders. How do you handle that? AV sync is interesting for a couple of reasons. The first reason is if you don't have a very precise AV sync algorithm, you're going to hear audio pops when you fail over from one encoder to another. The second reason is upon a resync, the system can potentially introduce a PTS discontinuity. It's actually 2 PTS discontinuities, an audio PTS discontinuity, which is an integer number of audio frames, and a video PTS discontinuity, which is an integer number of video frames. Those are going to be 2 different durations, so how do you do that without introducing AV sync error? Automated testing is interesting for a couple of reasons. We have integration tests that write a couple of output locked encodes to a static origin, and then we have a validation utility that can pull those encodes down, look at the actual media, and determine whether or not those encodes are output locked. How did we do that? And we spent a lot of time on unit testing as well, and I think we did a lot of great work there too. We implemented some really interesting debugging and troubleshooting features that I wish we had time to discuss. We implemented some features to improve interoperability with third-party packagers. And by working with multiple packagers, we've seen multiple approaches to how packagers handle encoder failover, and we could talk about those as well if we wanted to. Add insertion is interesting because it means that your segment lengths might not be a consistent length, and so how does output locking handle that? If you're not using add insertion and all of your segments are the same length, then maybe output locking isn't the right algorithm. Maybe you could use a different synchronization algorithm. We developed something called epoch locking, and what epoch locking does is instead of synchronizing to another actual encoder, it synchronizes to a hypothetical encoder that started on January 1st, 1970 at midnight UTC and has been running ever since. There are a couple of cool things about epoch locking. It plays nicely with dash segment templates, and it allows you to synchronize encoders even if they can't communicate with each other. We made some design decisions when we implemented output locking, And there are other designs we could have implemented instead, so we could talk about what are those alternate designs and what are the trade-offs involved. And there are also alternative applications of this technology. One example is, let's say you are responsible for streaming a 4K event, and you want to have an ABR stack with renditions from 4K all the way down to QSIF, but you have a problem. You can't find an encoder that has enough compute to encode all of those renditions in real time. One solution would be have one encoder encode the 4K rendition, another encoder encode the rest of the ABR stack, output lock those encoders together, and then you can simultaneously encode all of those renditions and have seamless ABR switching.
So yeah, and with that, if you are interested in helping us solve problems like these, Becky Moore from the AWS Elemental team is here. Becky said she was going to be in the audience somewhere. If she is, wave her hand. I can't see anything, but we'd love to talk to you if you're interested in working on problems like this alongside John and I. And I think we have time for 1 or 2 questions if any have come in via Slack. Knock, knock. Thank you. Hey, buddy.